This is the solution to the quarter horsepower motor power problem. So we have a quarter horsepower motor. First thing, we know this is going to be a power problem. It's usually easy to identify power problems. If you are looking for power or you see any units of power, you're going to use one of these two equations. Power equals work over time. And remember, there's lots of different ways you can get work. Okay, it's not just F cos theta delta X. You could find net work by change in kinetic energy, among other ways. But there's one formula, work over time, or in general, power is F times V. And remember, this could be an average power or an instantaneous power. To make it average, we can put bars over the word power and over V. So how do we know which one to use? So once we know we have a power problem, the question usually is going to deal at some point with a velocity if we're going to use the power as FV. So if you are given a velocity or the question is looking for a velocity, use the power as FV. That's the easiest one. And then all we have to do is if it's going to be an average or instantaneous. So this problem said a constant 28.6 centimeters per second. That means there's zero acceleration, so that means we're going to use V bar. So that means we will want to use for this problem average power equals F times V bar. So all we have to do now is put some numbers in. If we have 1/4 horsepower, when we do a conversion, we can't use 1/4 for power. It is 186.5 watts. So what do we have? And I'm going to abbreviate W for watts because I've never done that for work, mainly because the units of power are watts. We don't want to confuse work and watts. So we have 186.5 watts. Well, we don't know the lifting force, but we are given V bar. We have to convert that. 0.286 meters per second. You can't use centimeters per second. Everything has to be in standard units. So then we can find F. When you divide the two, you have F is 717, and we have to make sure we know the units. It's going to be newtons. We could prove it by doing a unit analysis of watts and meters per second, or if we know everything is hooked in right into our equation, we know the units of force are newtons. So we know the lifting force. This is not the answer to the question. This, in fact, is the force needed by the motor to lift. It is not the greatest mass that can be lifted. In fact, to get a little picture of understanding, what do we have? Well, really what we're looking at is pretend there's a motor way up here somewhere, and what we're doing is lifting an object of mass M. We are lifting. So we could pretend there's a rope on it. It doesn't matter. Here's the lifting force. The other force that acts on the object is mg. And the goal really is to figure the relationship between the two. Well, we want to call y up if we're lifting it. Believe it or not, even if we were lowering it, all we really need to know is the relationship between F and mg. Power developed by a motor is always positive. So we just need to really know what that force is. We can get it this way. Sum Fy equals MAY. So what do we have? F minus mg equals 0. The acceleration is 0 because it's at a constant speed. So now we know lifting force is equal to the weight of the object. So therefore we can find m. M is the lifting force over the acceleration due to gravity, which you can't use negative 9.8. That's not how mg works, if you remember. And when you do this, you get 73.2 kilograms. This is the largest mass that can be lifted.